Hey folks, morning. Monday morning here, day 4 for notes for us on November 9th. Yeah, a little different atmosphere here. Sorry, I ran out of time last night to be able to do this at the house, so I'm doing it here in school for you. So, all right. Today we're going to talk through just some more Atwoods and a concept called drag force as it relates to terminal velocity. Okay. The two pictures you have here on the left, that's Felix Baumgartner from Red Bull Stratus, who holds the world record for fastest speed by a human in free fall. On the right, Alan Estes, a Google exec who holds the record for highest free fall, and I think longest free fall and stuff like that. So I got some videos for you on those guys later on. All right. So here we go. When we talk about drag force and terminal velocity today, we're mostly going to be talking about drag force, okay? This describes when an object is falling faster and faster until air resistance basically stops it from accelerating, all right? And that's a big deal for us, meaning that initially, when we're looking at this, we're going to see that free fall produces an unbalanced force because you're going to continue to accelerate, okay? After a while, that drag force of that air actually starts to balance it out and it creates a balanced force situation. What I mean by that is that you're no longer accelerating. Okay? So drag is the resistance force exerted by a fluid on a moving object through the fluid. Now, a lot of people don't think of air as a fluid, but it definitely is a fluid. All right? If you've ever seen snowdrifts being made, how the wind goes over like a guardrail with snow in it and then creates that kind of spiraling effect and stuff like that. It does work that way. So water obviously is a pretty predictable fluid. So we ask the question, what affects drag? For us, these are 4 of the big things that affect drag. The shape of an object, right? If I drop a piece of paper, it's not going to fall very fast. If I crumple that piece of paper up, now it's a little bit more aerodynamic for us, all right? And that's the purpose behind like parachutes and stuff like that, is for them to grab as much wind as they can. But we don't want that in our cars as much as possible because, well, we want to slice through that air, so to speak. Relative speed of the fluid or the object. If you've ever driven into a headwind or walked into a headwind, you know that it's really, really more difficult to do. If you've walked with a tailwind or driven with a tailwind, you know that you get better gas mileage. It's a lot easier for us to do that. So, viscosity of the fluid is thickness of the fluid. Um, Cold water versus warm water. Cold water is actually a little bit thicker than warm water. Same thing with cold air versus warm air. Um, so when we see this, it may not be necessarily even the flow of it, um, just how thick that is, how close the molecules are together, all that good chem stuff. All right. Temperature of the fluid. Obviously, the higher the temperature of that fluid, the more excited the molecules are inside of that. The colder the fluid, obviously, the closer together, and also um, less less energetic they are. With viscosity, remember that's the ability to flow. I forgot about that. Sorry. Um, so if you think of like maple syrup coming out of the fridge, it's gonna be harder to get that thing to pour. If you put it in the microwave for a little bit, it'll be easier for it to pour. Okay. So when we look at forces at terminal velocity, drag force is a big one, meaning that our force of friction equals our gravity. Okay. So drag force is this concept. So when we see terminal velocity, and we'll talk some more about this tomorrow, all right, the drag force becomes equal to the object's weight, and that's something that we'll really, really kind of explore tomorrow. Okay, a belly flop skydiver, so all 4 arms kind of sticking out, both arms, both legs sticking out, stomach towards the ground. You're going to get to about 121 miles an hour. All right, once you hit terminal velocity where you can't speed up anymore. Aero Skydiver, think of like a pencil dive, but so everything's tight, but your nose is facing down towards the ground. That's going to get you up to 201 miles an hour. Joe Kittenger, he was the first really high altitude skydiver back in the 1960s, I believe. I got a video on the next slide. His story you want to see. From his glove having a hole in it and all kinds of stuff like, oh my goodness me, folks, it's insanity right there. Okay. But he got to about 614 miles per hour. Felix Baumgartner, Red Bull Stratus guy, got up to 834 miles an hour. He's the fastest ever. And Alan Estens, He got up to 822. Like I said, he was the one who got the world record for highest skydive. If you got some time and want to check some stuff out, check these out. They are honestly really, really good videos. They're on my channel. They're on my YouTube channel, so you'll be able to find them there and see them there. Okay. So that's kind of where we're going to stop with drag force and terminal velocity. We'll pick up again with that more tomorrow for that. Okay. All right. You're going to pause the video and you're going to try and check out this one. All right. So I want you to work through 1 and 2 and then try 3A and 3B. All right. This is kind of how we are going to ask this stuff for the quiz on Wednesday. Okay. So go ahead, pause video right now and check it out. All right. So here we go. For the first one, when we see, oh shoot, hold on. Let me fix this. This thing here should be, I missed one little thing. This should be 1,000 because it makes it a little better. Sorry about that. I know that's going to mess up your calculations. I apologize profusely for that. Okay. So what we see here is that at M1, which is this one, we got 250. At M2, we've got 1,000. All right. So with that one, M1 is a quarter of a kilogram. M2 is 1 kilogram. We got to change all that stuff into kilograms. Okay. Our acceleration due to gravity, 9.8 meters per second squared. Now, again, I just used the positive form of it. I'll make sure that I explain to you in each question here which one to use and so on and so forth. Okay. So our fun is going to be the mass 2 minus the mass 1. The reason is mass 2 is bigger. In a 2 hanging mass Atwood, the heavier mass is going to be the one that creates the movement. That means the 1,000 is going to go down. The 250 is going to go up. Okay. So we take our 1 times 9.8 and then we subtract off our 0.25 times 9.8. We see here our fun is 7.35 newtons. Okay. So that's how much unbalanced force we have going downwards. All right. We want to know what is the acceleration between the two masses. So now when we look at this, we've got our fun and we've got our M1 and M2. Between M1 and M2, now which one's going to move? The correct answer is both of them. All right. Because both of those will move, then what should happen is we should see our mass is the total of those two. All right. Whenever we're finding an acceleration of our Atwoods, it's extraordinarily likely that both of those will move. Okay. So we take 7.35 is equal to 1 plus 0.25a. We're going to take 7.35 divided by 1.25, and that's going to give us 5.8 meters per second squared. Point of emphasis here, this acceleration here always needs to be less than 9.8. Whenever we drop something, it cannot go faster than the speed of gravity, all right? Or the acceleration due to gravity, I should say, all right? If it does, that means that we've actually launched this projectile, okay? Which is not something we're going to do here, all right? 3, after half a second in an initial velocity of 0, what is the distance it takes? So our time is 0.5, our initial velocity is 0 meters per second, and our acceleration is 5.88 meters per second squared. We want to find the distance. Now, the distance it falls or the distance it rises, both are going to be exactly the same because remember, these are attached with a string. So in order for us to look at this, what we have to do is go through kinematics. All right, we could use the first kinematic, the third kinematic, the fourth kinematic. Because this thing has time, we're looking at the first and the fourth. Because it has an initial velocity, we're looking at the fourth one here. All right, so we start plugging information in. We see 0 is our initial velocity, half a second is our time, plus 1/2 5.8 times 0.5 squared. So basically what we'll do is we'll multiply all of those together with that 0.5 being squared at the end, and we'll find that our distance is 0.735 meters. Okay, so that's how far each one of them is going to move, so just shy of a meter. All right. Part B, how fast will it be traveling just before it hits the ground? We're still going to use all of our same good information, right? Because we know the time is legit, we know the velocity is legit. Hold on, let me turn on my lights. There we go. Okay. And our acceleration is 7.35, right? So then we look for our final velocity. All right, so for that one, we're just going to use the second kinematic. We could use the third kinematic if you wanted to use the distance with this information, then absolutely fine. I suppose, yeah, it's either the third or second. That's the only two that work, right? So we plug this stuff in, and this one's actually pretty not bad. All right, so we got 7.35 as our acceleration. we're going to take and multiply that by 0.5. We find that at the end, this thing's going to be going about 3.68 meters per second. So probably about 9 or 10 miles an hour, if that makes sense. All right. Now, would anything change if M1 and M2 were switched? Meaning that if M1 and M2 were different numbers. In this case, no, it's not going to. Nope, because it just means that the other side will move down and the other side will move up. That's all. Okay? All right. Try this one out. See if you can do this one as well. All right, so pause me and then get going. All right, here we go. Let's try it out. So you place a 250 gram mass on M1. So M1, remember, that is going to be this one right here. All right, because that one is right there, even though this is 1,000, all right, this is going to be a frictionless surface, which I'll make sure I add to it, okay? But because all of these things are frictionless, we know that that's going to cause movement, all right? So in this case, all of the fun is directly responsible from M1, okay? So what we find is we take the 0.25 times 9.8, all right? Our fun here is 2.45 newtons. Okay, what is the acceleration of the two masses? So now we know the fun, which was created by this one hanging here. Remember this one on the table? It's not going to move, at least due to gravity. Because of it not being able to move due to gravity, because the table's pushing back up against it. All right, so our fun is 2.45. What we're going to do is take 2.45 and divide it by both of those masses together, because both of them are going to move because they're both attached with a string. So we see our acceleration is about 1.96 meters per second squared. Again, it is under 9.8, so we're in a good place there. All right, the velocity after that, folks, this one's pretty similar to the previous one we just did. Delta D equals VIT plus 1/2 AT squared, 0 times 0.5 plus 1/2 times the acceleration times 0.5 squared. We find this thing should move about almost 1/4 of a meter. Okay, velocity again, same thing. We're going to use kinematic 2. 1.96 equals this. We're going to see this thing isn't moving real fast, okay, at 0.98 meters per second. All right. So then we ask the question, would anything change if M1 and M2 were changed? Absolutely. Yes, absolutely. All right. So try it out and see what changes. Okay. So go ahead, try it and run it. All right. Unbalanced force now. Oh, that's not right. Oh, wait. Yep. We're using the M1 because the M2 is now 0.25. Sorry, I got messed up there for a second. So now we got 1 times 9.8. So our fun is 9.8 newtons. All right. Which ones are going to move? Again, both of them. The difference being that with the higher amount of force from the 1,000 gram or the 1 kilogram mass 1, we should see this accelerates at a higher rate. And it does. 7.84, still under 9.8. So we're still good there with our calculations. Okay. Distance, just like we did before, all right, we're going to take our VI times our T, 1/2 the A we just calculated, and T squared. So 1/2 7.84 times 0.5 squared. This thing should travel almost a meter now, which is a lot more than what we saw previously. Again, higher acceleration, higher force of gravity, higher distance that this thing will fall. So if it traveled a further distance, should its final speed be faster? Absolutely, right? Just under a meter per second. Now we're almost 4 times as fast, right? Because we see this thing going quicker. All right. So these are what the Atwoods look like. I wanted to give you just another chance to see some of those and how I can work with problems. What I would say is now is homework time. Make sure you work through 4.1 here. You're going to have some time to be able to do that today. Tomorrow we start in on 4.2. Okay. Hope you folks have an absolutely fabulous day. Let me know if you got questions on Atwoods. Otherwise, I'll talk to you. Bye-bye.